All right, let's talk about OAuth 2.0. Now, I know it sounds like some super technical password you'd forget immediately, but trust me, by the end of this, you're going to think of it as something much simpler. The valet key for the entire internet.
You know these buttons. You see them everywhere. Log in with Google. Continue with Facebook. You click one and poof, you're magically signed into a brand new app. But have you ever stopped to think, how in the world does that work? How does that new app get your info without you ever typing in your Google password? That's the mystery we're going to solve today.
So the secret sauce here is a concept called delegated authorization. And this is where that valet key idea really clicks. Think about it. You give a valet a key, but it's a special key, right? It can start the car, maybe unlock the doors, but it can't get into your glove compartment or your trunk. You're giving limited, very specific permission. Well, OAuth 2.0 is exactly that, but for your digital life.
So let's really dig in and start with the core problem that OAuth was originally designed to fix.
Okay, so here's the classic scenario. Picture this. Years ago, if you wanted an app like LinkedIn to import all your contacts from Google, you might have had to give LinkedIn your actual Google username and password. I mean, that's just crazy, right? It's like giving a total stranger the master key to your entire house just so they can come in and water one plant. It's unbelievably risky.
And that's where OAuth 2.0 comes in to save the day. It's basically a universal rulebook, a standard protocol that lets different services talk to each other securely. It creates this trusted, really well-defined process where you, and only you, can grant one app permission to get specific data from another, all without ever handing over that master key.
So how does this digital valet key actually get made and used? Let's pop the hood for a minute and take a look at the most common workflow. The most common process is called the authorization code flow, and you can think of it like a four-step dance. First, the app you're using, let's call it the client, asks you for permission. It actually redirects you over to the service where your data is, like Google. That's the authorization server. Second, you see that familiar "Do you allow this app to?" screen, and you click Allow. Third, Google sends a temporary one-time use code back to the app. Now, this isn't the final key, it's more like a claim ticket. And finally, the app takes that claim ticket back to Google servers, proves it's the right app, and exchanges it for the real valet key, a secure access token.
Whoa, okay, this diagram might look a little complicated at first glance, but it's really just showing those four key players we just talked about. There's you, the user, who kicks the whole thing off. There's the client, which is the app asking for access. There's the authorization server, like Google, that checks with you and hands out the keys. And finally, the resource server, which is where your data actually lives, and it's the one that ultimately accepts that key.
Now, let's clear something up that trips up a lot of people: the difference between OAuth 2.0 and something called OpenID Connect. Here's the simplest way to think about it. OAuth is all about authorization, what you can do. It gives you an access token, which is like a key to a specific hotel room. OpenID Connect is built on top of OAuth, and it's for authentication, proving who you are. It gives you an ID token, which is much more like your passport. One's a key, the other's an ID. Okay, so we know what it is, we know how the basic flow works. Now let's zoom out a bit and see how this one simple idea has become the absolute security backbone for almost all modern software.
These days, big applications are built like Legos. They're broken down into dozens, sometimes hundreds of tiny independent microservices. And OAuth 2 is a perfect match for this world. Why? Well, first, it decouples security. You have one central server that handles all the authorization, so all the little services can just focus on their jobs. Second, you get this amazing granular control. A token can be scoped to allow a service to only read a user's name, but not touch their email or contacts. And finally, the tokens are usually stateless. All the info needed to verify the token is right there inside of it, which makes the whole system incredibly fast and easy to scale.
And we can actually see that lean and mean efficiency in the hard numbers. Because OAuth 2.0 is purely focused on that authorization piece, it's just plain faster. Compared to OpenID Connect, which has to do that extra work for authentication, OAuth has lower latency, uses less CPU, and has a smaller memory footprint. Now, those differences might look small, but when you're talking about millions of requests, they become absolutely massive.
And this chart really drives that point home. As the system gets busier and the number of user requests climbs, you can really see that performance gap start to widen. That latency for OAuth 2.0, that first bar, it just stays consistently lower. It proves that for systems that just need to know what you're allowed to do, it's the more efficient choice, hands down.
Next up, we're going to explore how this very same protocol is a key piece of the puzzle for one of the most important concepts in modern cybersecurity: something called zero trust.
The whole idea behind zero trust is actually pretty simple, but it's incredibly powerful. You see, old security models were like a castle with a moat. If you were inside the walls, you were trusted. Zero trust completely throws that idea out. It assumes threats could be anywhere, inside or outside. The model was simple. Trust nobody, assume everyone is a threat, and always verify. Every single request has to prove itself.
So, how does OAuth help make this happen? Well, it basically gives you the practical toolkit to enforce this philosophy. Those scope tokens we talked about, they limit the potential damage if a token gets stolen. You can also revoke access instantly if you detect a threat. You can make tokens that expire in just a few minutes, which shrinks the window of opportunity for an attacker. And then there's a feature called PKCE, which stands for Proof Key for Code Exchange. It adds another layer of security, kind of like a secret handshake, to make sure the right app is the one trading that code for a token.
All right, for our final section, we're going to look to the future. How does a protocol that was designed for humans clicking buttons adapt to a brand new world of autonomous AI agents? Just think about it for a second. The entire flow we've been discussing hinges on one critical thing: a human being, sitting at a computer, logging in and clicking allow. But what happens when an AI agent, running on some server in a data center, needs to access your Google Calendar to schedule a meeting all by itself? There's no person there to click the button. This is a huge, brand new challenge.
Well, the answer is just now starting to take shape, with new standards being designed for this exact problem. One of the big ones is the MCP authorization specification. It's basically an evolution of OAuth that leans heavily on that super secure PKCE mechanism we just mentioned to create a trusted process for these non-human machine-to-machine interactions.
So here's what makes PKC so critical for this new world. It's all about protecting the exchange itself. It guarantees that even if a bad guy somehow intercepts that temporary authorization code, they can't actually trade it in for the real access token. Why? Because they don't have a secret piece of information that only the original legitimate app has. It ensures that the party who started the request is the only one who can finish it. But, and this is a really important but, there's a critical limitation here. PKCE protects the process, but it doesn't actually prove who the client is in the first place. It doesn't solve that core identity problem. How do we know we should even be talking to this AI agent to begin with?
The solution is this fascinating idea called infrastructure asserted identity. Here's the big idea. Instead of the AI having its own username and password, its identity is proven by where it is running. Imagine an AI making a call from inside a secure bank vault. The server on the other end trusts the request not because the AI knows some secret password, but because the call is verifiably coming from inside that trusted vault. That's exactly what things like AWS roles or Kubernetes service accounts do. They act as that secure, verifiable location.
And this really brings us full circle. OAuth 2.0 started out as a clever way to manage trust between apps on behalf of us humans. Now it's evolving to create a new kind of trust for AI agents themselves. So the final question to leave you with is this. If an AI can have its own verifiable, secure identity, what does that really mean for the future of automation, for security, and for the very nature of what trust is on the internet of tomorrow?